The subject of star formation has undergone rapid development in the last few decades, spurred by instrumental advances that let us see deep into the regions where stars are forming. These regions are often obscured by dust and invisible to us, invisible light, requiring long infrared wavelengths or radio waves to penetrate. Our ideas of star formation historically were too simple. We imagined a nearly spherical and diffuse cloud of gas slowly rotating, collapsing along its pole, forming a disk, planets form, the bulk of the material goes into a central star that switches on fusion. In practice, star formation is more complex because it occurs in large volumes of space where many stars form. Those stars interact with each other and with the gas out of which they're made and the gas left over from their formation. We've only just discovered how complex this situation really is. You can think of it as analogous to human beings. Most of the people you meet out there in the world are middle-aged or youngish. We rarely see people being born, and we rarely see the death of people. These are hidden from view and occur in particular places. So it is with stars. Most of the stars we see are middle-aged or in the heart of their lifetimes. The transient stages of star birth and death are difficult to observe and have only been observed with different techniques expanding the electromagnetic spectrum. Here, as a typical example, is the 30 Doradus star formation region, a stellar nursery where thousands of stars are forming as we speak. This region, however, is in the Large Magellanic Cloud at a distance of 170,000 light-years from the Earth. Zooming in from the view through optical light to what you might see with the Hubble Space Telescope at infrared wavelengths, drilling down into the central star cluster, we can see just how multiscale and complex star formation really is. Advances in computing have greatly assisted our understanding of star formation, now that we know it's not a simple spherically symmetric process. In this computer simulation from Matthew Bate, we can see a region where many stars are forming. We can watch the coalescing gas, the swirling regions of turbulence and convection, and then the places where gravitational collapse, in a nearly spherical sense, forms stars. Those young stars emit a lot of high-energy radiation, which blows out residual gas from their formation. We can also see that the newly formed stars are in complex orbital patterns, occasionally being flung from the system where they were formed. The entire process here takes perhaps tens of millions of years, a fairly rapid time sequence in the history of a star like the Sun that is now billions of years old. As an example of star formation that we can see with the naked eye in our night sky in the winter in the northern hemisphere, but more easily in the southern hemisphere, consider the Orion Nebula. Viewed in optical light, we cannot see the star cluster, where high-mass stars are ferociously forming from the condensing gas. Such a view is only possible at infrared or even longer wavelengths. The difference between the infrared and optical views of Orion and the Orion Nebula are dramatic. The reason for this is the very different properties of electromagnetic radiation of different wavelengths with respect to dust. Looking towards the center of a region of star formation with visible light is like looking through a closed door. Barely 1 in 1,000 or even 1 in a million photons can escape the dusty region. But infrared waves interact much more weakly with the typical micron-sized dust particles in interstellar space. So infrared waves penetrate, and therefore we can see deep into these star-forming regions. Here's a three-dimensional visualization using actual data from the Hubble Space Telescope of what it would be like to fly through the Orion star-forming region. The colors are indications of the chemical elements contained in the enriched gas, which has a lot of oxygen, neon, as well as the abundant hydrogen and helium. The Hubble Space Telescope and the Spitzer Space Telescope together have given us detailed views of regions of star formations. Eta Carina is another nebula where we've seen in detail using the Hubble and Spitzer Space Telescopes exactly how stars are forming, even at the present day. Some of the youngest stars in this region are younger than the human race, barely 1 million years old. With infrared data, we can even fly deep into the star formation region, seeing it in detail. It's fairly likely that star birth and star death are connected, intimately. There's a mechanism called induced star formation, whereby the event that triggers the collapse of a diffuse cloud in space containing gas and dust but no stars is the death of a nearby star. The shock wave emerging from that supernova event will compress the edge of the nearby gas cloud, and that can induce gravitational collapse. We have a fair degree of certainty that such events are occurring in the nearby universe. There's even indirect evidence, somewhat disputed, that our solar system formed in this way because of the death of a nearby star over 4.5 billion years ago. Within these collapsing regions, a young star forms, incorporating 99.9 or more % of the available material. What's left, the residue, forms rocky planets and gas giants, and we now know that this process, the process of planet formation around a new star, is commonplace. Computers can simulate the formation of stars and their surrounding planets with a fairly high degree of accuracy. It's interesting that star formation is not completely efficient. If 100% of the mass collapsed into the central object, there would be no material left over for planets. Telescopes in space, and particularly infrared observations, have given us a more nuanced view of the complexities of star formation. Star formation is not the simple spherical collapse of a gas cloud. It can be triggered by the death of nearby stars, and it usually occurs in large regions where dozens, hundreds, or maybe even thousands of stars are forming simultaneously, in chaotic swirling regions of convection, where interactions among the newly formed stars occasionally eject them from the system.